66 million years ago, the Earth was a very different place. The continents were not arranged as they are today. Vast inland seas cut through entire land masses, and warm, shallow waters spread across regions that are now dry and distant from any ocean. There were no polar ice caps. Even at the far edges of the planet, the climate remained mild, and the air itself carried more warmth than it does now. Sea levels were higher, and much of the land lay low and humid beneath a heavy sky. Dense forests stretched across the continents, filled with unfamiliar plants, early flowering species, and thick layers of vegetation that thrived in the constant warmth. The world moved slowly, shaped by heat, water, and time. It was a planet full of quiet stability. And within this world, life had reached a kind of balance, an equilibrium that had taken millions of years to form. Among the forests and along the edges of these vast inland seas, large shapes moved steadily through the landscape. Herds of herbivorous dinosaurs passed through dense vegetation, feeding as they went, their movements unhurried and deliberate. In the distance, predators followed, not in constant pursuit, but as part of a rhythm that had long defined this world. This was the Late Cretaceous, the final chapter of the dinosaurs. And for a long time, it seemed as though this world would continue unchanged. Before we continue, take a moment to consider, where are you watching from which country, and how far removed it is from the final days of the Cretaceous when life moved as if the world would go on unchanged. If this atmosphere draws you in, consider subscribing to follow the journey ahead. It's always intriguing to sense how far these stories reach. Dim the lights, settle into stillness, and let the present dissolve into a warm, ancient landscape, where distant calls echo through dense vegetation and the soft rustle of leaves carries a world just before its final turning. The consequence was a world with substantially higher sea levels between 100 and 200 meters above the present, and a continental arrangement still reorganizing from the long breakup of the supercontinent Pangaea. Warm equatorial waters circulated more freely between ocean basins, reducing the temperature gradient between equator and poles and producing a climate that was not only warmer overall, but more uniform across latitudes. Precipitation was broadly distributed, sustaining dense vegetation from the tropics well into polar regions, a condition confirmed by fossil plant material recovered from sites in Alaska, Greenland, and Antarctica. On land, river systems fed by abundant rainfall flowed across low-gradient floodplains, depositing the thick sedimentary sequences now preserved as major fossil-bearing formations, among them the Hell Creek Formation in western North America, the Maastricht Formation in Europe, and the Nemegt Formation in Central Asia. These geological archives preserve not only the remains of organisms, but detailed records of the environments in which they lived. It was within this physical world, warm, humid, partially flooded, and blanketed by expansive vegetation, that the dinosaurs had come to define the living landscape. Their history within it was long. Dinosaurs had first appeared approximately 230 million years ago during the Triassic period, emerging from a broader group of archosaur reptiles in the aftermath of the Permian-Triassic extinction, the most severe mass extinction in Earth's history, which had cleared ecological space across both land and sea. From modest beginnings as relatively small, bipedal animals, dinosaurs had diversified across the subsequent Triassic and Jurassic periods into an extraordinary range of body forms, sizes, and ecological strategies. By the time the Cretaceous began, roughly 145 million years ago, they had already been the dominant large-bodied vertebrates on land for tens of millions of years. The Late Cretaceous was not the beginning of their story. It was its final and most elaborate chapter. By 66 million years ago, dinosaurs occupied ecological roles across virtually every terrestrial environment on the planet. Large herbivores fed on different layers of vegetation, from low ground cover to mid-height shrubs and the lower branches of trees. Carnivores ranged from small, agile hunters of invertebrates and small vertebrates to massively built apex predators capable of subduing prey of several metric tons. Omnivores and generalist feeders occupied the ecological space between. This diversity of form and function was the product of more than 160 million years of evolutionary refinement of anatomical and physiological adaptations accumulated across an interval of time so long that it dwarfs the entire history of our own genus by a factor of more than 100. Evidence from bone microstructure, isotopic analysis, and comparative anatomy indicates that many dinosaur lineages maintained elevated metabolic rates and rapid growth trajectories, with some groups showing a degree of endothermic heat regulation that distinguished them clearly from the cold-blooded reptiles with which they were long and inaccurately compared. These physiological characteristics allowed dinosaurs to sustain activity across a broad range of environmental conditions and to grow to body sizes that placed them among the largest terrestrial animals in Earth's history. They were not simply large reptiles tolerating a warm world. They were active, physiologically sophisticated animals whose biology was integrated with the specific conditions of the Cretaceous environment in ways that had been refined across an immense span of evolutionary time. The ecosystems they inhabited were not static. Species distributions shifted in response to changes in temperature, precipitation, sea level, and plant community composition. Local extinctions and recolonizations were part of the ongoing ecological history of the Cretaceous world. And yet, by the final stages of the period, the broad structure of late Cretaceous life had been stable long enough to produce ecosystems of considerable internal coherence biological communities in which the relationships between species and their physical environment had been tested and reinforced across millions of years of shared evolutionary history. The animals that moved through the forests and across the floodplains of the late Cretaceous were products of that coherence. They were shaped by it, sustained by it, and in ways that only the subsequent geological record would reveal vulnerable to forces that lay entirely outside the range of variation this world had previously encountered. The land of the late Cretaceous was not empty space between predator encounters. It was a continuously functioning biological system, and at its most visible level, moved some of the largest animals that have ever walked the surface of the Earth. Among the most widespread and ecologically significant of these were the hadrosaurs, the duck-billed dinosaurs. By the final stages of the Cretaceous, hadrosaurs had become the dominant large herbivores across much of the Northern Hemisphere. They were not a single species but a diverse family represented by dozens of distinct genera distributed across North America, Asia, and Europe. Individual animals ranged from approximately 7 to 12 meters in length and weighed between 2 and 4 metric tons in most species, though some larger representatives may have exceeded that range. They moved on 2 legs when traveling at speed, dropping to all 4 when feeding or moving slowly across open ground. Their most distinctive anatomical feature was the structure of their jaws and teeth. Hadrosaurs possessed what paleontologists describe as a dental battery, a tightly packed arrangement of hundreds of teeth organized into functional columns, with replacement teeth continuously developing beneath those in active use. At any given time, a hadrosaur carried between 300 and 1,000 individual teeth in its jaws, depending on the species. This system allowed for the continuous, high-volume processing of tough plant material. As surface teeth wore down through contact with abrasive vegetation, new teeth moved upward to replace them. The result was a grinding surface of considerable efficiency, capable of breaking down fibrous stems, coarse leaves, and woody material that would have been inaccessible to animals with simpler dental arrangements. This feeding capacity had direct ecological consequences. Hadrosaurs could exploit a wide range of plant material across different vegetation layers, from low ground cover to mid-height shrubs and the lower branches of trees. Evidence from fossilized stomach contents and coprolites preserved digestive remains indicates a diet that included conifer needles, flowering plant material, seeds, and woody fragments. Their ability to process such varied material made them highly adaptable across the diverse plant communities of the late Cretaceous landscape. Hadrosaurs are also among the best evidenced dinosaurs in terms of social behavior. Bone bed sites where the remains of multiple individuals are preserved together have been documented across several formations in North America and Asia. Some of these sites contain the remains of hundreds of individuals of varying age and size, suggesting that hadrosaurs moved in groups. Whether these groups constituted true migratory herds or represented seasonal aggregations at specific feeding or nesting sites remains a subject of ongoing research, but the physical evidence is consistent with gregarious behavior of some kind. Nesting sites attributed to hadrosaurs have also been identified, with clutches of eggs and the remains of juveniles found in proximity to adult individuals, suggesting a degree of site fidelity and possibly parental association during early development. Alongside the hadrosaurs, the ceratopsians, the horned dinosaurs, formed another major component of the large herbivore community, particularly in western North America. Triceratops, among the last and largest of the ceratopsian lineage, is among the most abundantly represented dinosaurs in uppermost Cretaceous deposits. Individual animals reach lengths of approximately 8 to 9 meters and weights estimated between 6 and 12 metric tons, making them among the heaviest land animals of their time. Their skull alone could measure more than 2 meters in length, bearing a prominent frill of bone extending from the back of the head and 3 facial horns, 2 above the eyes and 1 on the nose, that varied in size and curvature between individuals and across growth stages. The functional role of these structures has been debated extensively. The horns show evidence of wear and damage consistent with use in physical contact, and some specimens preserve healed injuries on the frill and facial region attributable to horn strikes. This supports the interpretation that ceratopsian horns were used in intraspecific contests, competition between individuals of the same species, likely related to access to mates or resources. The frill, richly supplied with blood vessels based on vascular channel traces preserved in fossil bone, may have functioned in display, in thermoregulation, or both. The two functions are not mutually exclusive, and current evidence does not fully resolve the question. Ceratopsians were browsers and grazers, with a distinctly different feeding apparatus from the hadrosaurs. Their beaks were narrow and blade-like at the tip, adapted for cropping vegetation selectively rather than processing large volumes of mixed material. Behind the beak, shearing teeth arranged in vertical batteries sliced through plant matter rather than grinding it. This dietary strategy made ceratopsians well-suited to tougher, more fibrous vegetation, including low-growing cycads, ferns, and the stems of flowering plants that were becoming increasingly common across late Cretaceous landscapes. Beyond the hadrosaurs and ceratopsians, the ankylosaurs represented a third major group of large herbivores. These were heavily armored animals, covered across the back and flanks with a layer of bony plates and nodules embedded in the skin, a structure known as osteoderms. In the ankylosaurid lineage, the tail terminated in a large, solid club of fused bone that could be swung with considerable force. Estimates based on muscle attachment sites and bone structure suggest that this tail club was capable of delivering impacts sufficient to fracture bone, making it an effective deterrent against large predators. Ankylosaurs were low-bodied animals, typically ranging from 5 to 8 meters in length, with wide barrel-shaped torsos adapted for processing large quantities of low-nutrient vegetation. Their teeth were simple and leaf-shaped, suited to cropping rather than extensive mechanical processing, suggesting that fermentation within a large digestive tract may have played a significant role in breaking down plant material. The sauropods, the long-necked dinosaurs that had dominated herbivore communities during the Jurassic period, were less prominent across much of the Late Cretaceous Northern Hemisphere, where hadrosaurs and ceratopsians had largely displaced them in ecological terms. However, sauropods remained abundant and diverse in the Southern Hemisphere. In South America, Titanosaur sauropods continued to reach extraordinary body sizes. Patagotitan majorum, recovered from deposits in Argentina dating to the mid-Cretaceous, is among the largest animals estimated to have ever lived on land, with a body length approaching 37 meters and a mass estimated between 60 and 70 metric tons. While the latest Cretaceous sauropods of the Southern Hemisphere were not all this large, titanosaurs of substantial size persisted through to the end of the period, occupying the role of bulk vegetation processors in ecosystems where they remained the dominant large herbivores. The landscapes that supported these animals were defined by their capacity to sustain enormous quantities of plant biomass. The warm, humid conditions of the late Cretaceous produced vegetation that was dense, fast-growing, and distributed across a wide latitudinal range. Floodplains along river systems supported thick stands of vegetation renewed regularly by seasonal flooding and sediment deposition. Upland regions carried conifer-dominated forests interspersed with ferns, cycads, and an increasing diversity of flowering plants. The physical structure of these environments, the vertical layering of vegetation from ground cover to canopy, the horizontal variation between open floodplain and closed forest, created a mosaic of feeding opportunities that different herbivore body plans were suited to exploit in different ways. Large herbivores, by the nature of their energetic requirements, consumed plant material at rates that had direct effects on the vegetation around them. A single large hadrosaur, maintaining a body mass of 3 to 4 metric tons, with the elevated metabolic demands suggested by current evidence, would have required substantial daily caloric intake. Multiplied across herds of dozens or hundreds of individuals, this consumption shaped plant community structure in ways broadly analogous to the effects of large herbivore herds documented in modern ecosystems. Vegetation was selectively reduced in areas of heavy use, promoting regrowth of pioneer species and maintaining open patches within otherwise dense plant communities. Trampling and soil disturbance associated with large animal movement further influenced water infiltration, seed dispersal, and nutrient cycling at the local scale. The relationship between large herbivores and the landscapes they occupied was, in this sense, mutually constitutive. The animals were products of environments capable of sustaining them, and those environments were, in turn, shaped, at least in part, by the animals moving through them. This interdependence had developed across millions of years of coevolution between animal communities and plant communities, producing, by the late Cretaceous, a system of considerable biological complexity, one in which the removal or significant alteration of any major component would have cascading effects through the rest of the ecological network. These animals did not exist in isolation from one another or from the physical conditions around them. They were embedded in a landscape defined by heat, moisture, and biological abundance, a world in which the conditions for large-bodied life had been in place long enough to produce animals of extraordinary size, diversity, and ecological reach. The presence of large herbivores in such abundance was not a condition that existed in ecological isolation. Where plant biomass supported animals of several metric tons, and where those animals moved in groups across open floodplains and through dense forest margins, predators of corresponding scale had evolved to occupy the upper levels of the food web. The Late Cretaceous was not a world defined by its herbivores alone. It was a world structured, in significant part, by what hunted them. Among the predators of the Late Cretaceous, Tyrannosaurus rex stands as the most extensively studied. Its remains are known from the Hell Creek and Lance formations of western North America, deposits laid down in the final 2 million years before the end Cretaceous extinction. Individual animals reached lengths of approximately 12 to 13 meters and body masses estimated between 8 and 14 metric tons, making Tyrannosaurus one of the largest terrestrial predators in the fossil record. Its skull alone measured up to 1.5 meters in length and was constructed with a robustness unusual even among large theropods, thick bone, reinforced joints, and a kinetic structure that allowed the upper jaw elements to flex slightly under load, distributing the mechanical stress of biting across a wider area of the skull. The bite force of Tyrannosaurus has been estimated through biomechanical modeling of jaw musculature and bone geometry. Current estimates place maximum bite force at between 35,000 and 57,000 newtons at the back teeth, a value that exceeds the estimated bite force of any other known terrestrial predator, living or extinct. The teeth themselves were not blade-like, as in many other large theropods, but thick, conical, and deeply rooted, described by researchers as more consistent with crushing than slicing. Fossil bones from prey animals, including hadrosaurs and ceratopsians, have been recovered with puncture marks and deep grooves attributable to Tyrannosaurus teeth, and some of these bones show evidence of having been bitten through entirely. Coprolites, fossilized feces attributable to large tyrannosaurids, contain crushed and partially digested bone fragments, confirming that bone consumption was a regular component of the feeding behavior. Whether Tyrannosaurus was primarily a predator or a scavenger has been a persistent question in paleontological literature. Current evidence supports the conclusion that it was predominantly an active predator capable of taking large prey, while also consuming carcasses opportunistically, a behavioral pattern consistent with large carnivores in modern ecosystems. Healed bite marks on the bones of prey animals indicate that at least some individuals survived initial attacks, which is more consistent with predation attempts than with scavenging of already dead animals. Trackway evidence, though limited, suggests locomotion at speeds consistent with pursuit over short distances rather than sustained high-speed running. Biomechanical analyses of leg proportions and muscle mass estimates place comfortable walking speeds at approximately 4 to 5 kilometers per hour, with maximum speeds likely in the range of 17 to 25 kilometers per hour, sufficient for pursuit of large, relatively slow-moving herbivores across open ground. Tyrannosaurus did not stand alone as the apex predator of its region. Across the broader Late Cretaceous world, other large theropods occupied equivalent ecological roles in different geographic areas. In Asia, Tarbosaurus bata, closely related to Tyrannosaurus and of comparable body size, was the dominant large predator of the Nemegt Formation ecosystem in what is now Mongolia. In South America, abelisaurid theropods such as Carnotaurus sastre filled the large predator niche characterized by shorter, more robust skulls, reduced forelimbs even more vestigial than those of tyrannosaurids, and body proportions that suggest different locomotor and prey capture strategies. In Europe, the predator fauna was distinct again, reflecting the island geography of that region and the isolation it imposed on evolving animal communities. Below the apex predators, a second tier of smaller theropods occupied the mid-level predator roles within late Cretaceous ecosystems. The dromaeosaurids, commonly referred to as raptors, were among the most ecologically significant of these. Animals such as Dacotaraptor, recovered from Hell Creek Formation deposits, reached lengths of approximately 5 to 6 meters and combined a lightly built body with elongated hind limbs, a stiffened tail for balance during rapid movement, and the enlarged, recurved claws on the second toe that characterize the family. Current interpretations of dromaeosaurid predatory behavior emphasize the use of these claws not primarily for slashing, but for gripping and pinning prey, a restraint and bite strategy analogous to that employed by modern raptorial birds, to which dromaeosaurids are closely related. Evidence of feathering in dromaeosaurids is well established from exceptionally preserved specimens in Asia, and it is reasonable to infer that North American relatives were similarly feathered, though direct evidence from those deposits is limited by preservation conditions. Troodontids represented another component of the mid-level predator guild. These were smaller, lightly built theropods with relatively large brain-to-body ratios compared to other dinosaurs, a feature inferred from endocranial casts that preserve the approximate shape of the brain cavity. Their large, forward-oriented eye sockets suggest well-developed binocular vision, and some species may have been capable of activity in low-light conditions. Their diet likely included small vertebrates, invertebrates, and possibly plant material, placing them in an omnivore role rather than strict predation. The relationship between predators and prey in late Cretaceous ecosystems was not simply one of pursuit and capture. It was a set of interdependent pressures that shaped the anatomy, behavior, and ecology of both sides over millions of years. The heavy armor of ankylosaurs, the horns and frills of ceratopsians, the gregarious behavior inferred for hadrosaurs, these features did not develop independently of predation pressure. They reflect a long history of evolutionary response to the presence of large, capable predators in shared environments. Predator population densities were, by biological necessity, far lower than those of their prey. Energetic constraints dictate that each successive level of a food web supports fewer individuals than the level below it. A large predator such as Tyrannosaurus required substantial caloric intake to maintain its body mass. Estimates based on reptilian and avian metabolic scaling suggest annual food requirements in the range of tens of thousands of kilograms of meat, though uncertainty remains around the precise metabolic rate of tyrannosaurids. Fossil evidence from Hell Creek Formation deposits suggests that Tyrannosaurus individuals were relatively rare on the landscape, consistent with the low population densities expected for large apex predators in functioning ecosystems. Juvenile tyrannosaurids occupied a different ecological position from adults. Younger animals were significantly smaller and more lightly built, with proportionally longer legs and more blade-like teeth than the robust adults. This has led some researchers to propose that juvenile and adult tyrannosaurids effectively occupied different predator niches within the same ecosystem, juveniles targeting smaller, faster prey while adults focused on the large herbivores. Their body size and jaw strength were suited to subdue. If accurate, this would represent a form of ontogenetic niche partitioning that reduced direct competition between age classes of the same species and increased the overall predatory efficiency of the tyrannosaurid lineage within its ecosystem. The predator community of the late Cretaceous was therefore not a simple hierarchy, but a layered and functionally differentiated system in which animals of different sizes, speeds, and feeding strategies divided the available prey resource across multiple ecological dimensions. This structure had developed through millions of years of coevolution between predator and prey lineages, producing by the end of the Cretaceous a predator fauna of considerable diversity and ecological integration, one whose stability depended, as all such systems do, on the continued functioning of the broader environmental conditions that sustained it. The land surface of the Late Cretaceous represented only a portion of the biosphere. Across much of the planet, shallow epicontinental seas spread over flooded continental margins, and deeper open ocean basins extended between the drifting landmasses. These marine environments were not peripheral to the story of the Cretaceous world. They were among its most productive and biologically complex zones, sustaining food webs of considerable depth and supporting some of the largest predatory animals the planet has ever produced. The chemistry of late Cretaceous oceans differed from today's in several important respects. Water temperatures were substantially elevated, with sea surface temperatures in tropical regions estimated at between 30 and 35 degrees Celsius, several degrees warmer than modern tropical oceans. Even at higher latitudes, sea surface temperatures remained mild, consistent with the broader absence of polar ice and the elevated greenhouse gas concentrations that characterized the period. This thermal state influenced ocean circulation, biological productivity, and the distribution of marine organisms across latitudinal gradients. Oxygen levels in deeper ocean layers were periodically reduced during the Cretaceous, a condition referred to as oceanic anoxia. Several oceanic anoxic events are recorded in the geological sequence of the Mesozoic, marked by distinctive, dark, organic-rich sedimentary layers known as black shales. These events, driven by a combination of elevated temperatures, reduced circulation in deeper waters, and high biological productivity in surface layers, resulted in the widespread deposition of organic carbon on the seafloor rather than its decomposition and recycling. By the late Cretaceous, the most severe of these anoxic episodes had passed, but the ocean retained characteristics of a warm, stratified system in which deep-water oxygen replenishment was less efficient than in the modern ocean. The shallow epicontinental seas, including the western interior seaway of North America and the fragmented marine environments of Europe, were among the most biologically productive regions of the late Cretaceous world. Shallow water allows sunlight to penetrate to the seafloor, supporting photosynthetic organisms across a greater portion of the water column than is possible in deep ocean environments. Nutrient-rich sediments delivered by river systems from surrounding landmasses further enhanced productivity in nearshore zones. The result was a marine environment of high biological activity, supporting diverse communities of invertebrates, fish, and the large marine reptiles that occupied the upper levels of the food web. Among the most ecologically dominant of these marine reptiles were the mosasaurs. These were not dinosaurs, but large, fully aquatic lizards belonging to a lineage that had transitioned from terrestrial ancestors to an entirely marine existence during the Cretaceous period. By the late Cretaceous, mosasaurs had diversified into a wide range of body sizes and feeding strategies, becoming the dominant large predators across most of the world's shallow seas. The largest known mosasaur genera among them, Mosasaurus and Tylosaurus, reached lengths of 13 to 17 meters. Their bodies were elongated and laterally compressed, propelled by a powerful tail fin and stabilized by 4 paddle-like limbs modified from the limbs of their terrestrial ancestors. Their jaws were long, lined with conical teeth, and in some species equipped with a secondary set of teeth on the palate, the pterygoid teeth, which prevented prey from escaping once seized. Mosasaurs occupied a range of predatory roles within the marine ecosystem. Larger species fed on fish, other marine reptiles, and large invertebrates, including ammonites, the coiled cephalopods that were abundant in late Cretaceous seas. Smaller mosasaur species targeted softer prey, and some genera show dental adaptations consistent with crushing hard-shelled organisms such as mollusks. Bite marks attributable to mosasaurs have been identified on ammonite shells and on the bones of other marine vertebrates, providing direct physical evidence of predatory interactions. The diversity of feeding strategies across the mosasaur family indicates that different species partitioned the available prey resource across multiple ecological dimensions, reducing direct competition within a guild that had, by the latest Cretaceous, become remarkably species-rich. Alongside the mosasaurs, plesiosaurs continued to inhabit late Cretaceous seas, though their diversity had declined relative to earlier periods. Plesiosaurs were an older lineage, having first appeared in the early Jurassic, and by the late Cretaceous they were represented primarily by two body forms. The elasmosaurids were long-necked forms with small heads and compact bodies, their necks comprising more than half of total body length in some species and containing as many as 70 cervical vertebrae. Elasmosaurus platyurus, from the Pierre Shale of North America, reached an estimated total length of approximately 14 meters, with a neck accounting for roughly 7 meters of that length. The polycotylids, by contrast, had shorter necks and larger heads, a body plan convergent in some respects with that of the mosasaurs and likely suited to different prey capture strategies. The feeding ecology of long-necked plesiosaurs has been the subject of considerable discussion. Early interpretations propose that the long neck functioned as a surface skimming device sweeping through schools of fish. More recent biomechanical analysis suggests that the neck was not highly flexible in the vertical plane, limiting the animal's ability to raise or lower its head dramatically relative to its body. Current hypotheses favor an interpretation in which elasmosaurids used their long necks to approach prey from a distance while keeping the bulk of their body and the hydrodynamic disturbance it created further away, allowing for a degree of stealth in approach before a strike. Stomach contents preserved in some plesiosaur specimens include fish remains, small cephalopods, and in some cases gastroliths, smooth stones swallowed and retained in the digestive system, possibly to aid in processing prey or to provide ballast during diving. The open ocean beyond the shallow epicontinental seas was inhabited by a distinct but overlapping set of organisms. Large bony fish, including members of the family Geophragtinus, reached lengths of up to 6 meters and were abundant predators in the water column of the western interior seaway. Geophragtinus specimens preserved with intact stomach contents have been recovered, including one famous specimen containing the nearly complete skeleton of a 1.8-meter fish of a different species, providing direct evidence of predatory behavior. Sharks were present throughout the late Cretaceous oceans, though the largest shark lineages familiar from later geological periods had not yet appeared. Cretaceous sharks occupied mid-level predator roles within the marine food web, feeding on fish, cephalopods, and invertebrates. The base of the marine food web rested on communities of microscopic photosynthetic organisms, primarily coccolithophores, dinoflagellates, and diatoms, that formed the foundation of oceanic productivity. Coccolithophores, single-celled algae that produce intricate calcium carbonate plates, were particularly abundant during the Cretaceous and contributed significantly to the thick chalk deposits that accumulated on seafloors across parts of Europe and elsewhere during this period. The White Cliffs of Dover in England and the broader chalk formations of northwestern Europe are composed largely of the accumulated remains of these microscopic organisms. Their calcium carbonate plates settling continuously to the seafloor over millions of years to form deposits tens to hundreds of meters thick. This biological productivity at the base of the food web sustained the entire structure above it, from small invertebrates and filter feeders through mid-level fish and cephalopods to the large marine reptiles at the apex. The late Cretaceous ocean was therefore not a uniform environment, but a layered and regionally variable system structured by depth, temperature, light availability, and nutrient supply. Its biological communities had developed across millions of years of marine evolution into assemblages of considerable ecological complexity, ones in which the interactions between organisms at different levels of the food web were tightly integrated and mutually dependent. The seas of the late Cretaceous were, in this sense, as fully realized a biological world as the land surface above them. The marine ecosystems of the late Cretaceous were not sustained by the large predators alone. Behind the mosasaurs and plesiosaurs, and beneath the surface layers where large bony fish pursued their prey, lay a biological architecture of considerable depth, a series of interconnected feeding relationships that extended from the sunlit surface waters down through the water column to the seafloor, and that had been developing in complexity across tens of millions of years of ocean evolution. To understand the predatory life of these ancient seas, it is necessary to look not only at the largest animals within them, but at the full range of hunting strategies, body forms, and ecological roles that define the marine food web from its middle layers upward. Among the most successful mid-level predators of the late Cretaceous ocean were the sharks. Though the lineages most familiar from the modern ocean, including the ancestors of the great white shark, had not yet reached their later size or diversity, Cretaceous sharks were nonetheless abundant, varied, and ecologically significant. Cretoxyrhina mantelli, sometimes referred to informally as the Ginsu shark, was among the largest of the late Cretaceous sharks, reaching estimated lengths of 6 to 7 meters. Its teeth were large, smooth-edged, and laterally compressed, well suited to cutting through flesh and bone rather than gripping and holding prey. Fossil evidence places Cretoxyrhina in direct predatory interaction with a range of large marine vertebrates. Shark teeth attributable to this species have been found embedded in the bones of mosasaurs, plesiosaurs, and large bony fish, and at least one specimen of the large fish Xiphactinus has been recovered with Cretoxyrhina teeth marks on its vertebrae. These physical associations confirm that Cretoxyrhina was not restricted to small prey, but was capable of attacking animals of substantial size. Squalicorax was another abundant shark of the late Cretaceous, smaller than Cretoxyrhina at approximately 2 to 3 meters in length, but represented by a greater number of fossil specimens across a wider geographic range. Its teeth were serrated and recurved, more similar in form to those of modern carcharonid sharks than to the blade-like teeth of Cretoxyrhina, and this dental morphology is consistent with a diet that included both active prey and opportunistic scavenging of carcasses. Squalicorax teeth have been found associated with the bones of marine reptiles, large fish, and even terrestrial animals, including dinosaurs, whose remains apparently entered the marine environment through river transport or coastal proximity. This breadth of association suggests a generalist predatory and scavenging strategy that would have made Squalicorax a consistent presence across a wide range of marine environments and conditions. The cephalopods occupied a different but equally important role within the late Cretaceous marine ecosystem. Ammonites externally shelled cephalopods, distantly related to the modern nautilus, were among the most abundant and diverse marine invertebrates of the Mesozoic. By the late Cretaceous, ammonite diversity had already begun to decline from earlier peaks, but hundreds of species remained in existence across the world's oceans, ranging in shell diameter from a few centimeters to, in the case of the largest Paraposocene ammonites, more than 2 meters. Ammonites occupied primarily the water column and shallow seafloor environments, feeding on plankton, small invertebrates, and organic particles. Their abundance made them a critical intermediate link in the marine food web, consuming primary producers and small invertebrates at one level and serving as prey for sharks, mosasaurs, and large fish at another. Belemnites, squid-like cephalopods with an internal calcified structure called a guard, were similarly abundant and served an analogous ecological role. Unlike ammonites, belemnites lacked an external shell and were more mobile in the water column, likely forming large aggregations that made them accessible prey for a wide range of predators. Their guards preserve well in the fossil record, and their abundance in many Cretaceous marine sediments reflects the enormous populations these animals maintained. Some marine reptile stomach contents and coprolites contain concentrations of belemnite guards, confirming their importance as a prey resource. At deeper levels of the water column and along the seafloor, communities of invertebrates form the structural base of the benthic food web. Bivalves, gastropods, echinoderms, and crustaceans populated the seafloor in communities whose composition varied with water depth, sediment type, and oxygen availability. In well-oxygenated shallow water environments, these communities were diverse and densely populated, providing a food resource for bottom-feeding fish, rays, and small marine reptiles. In deeper or more poorly oxygenated zones, benthic diversity decreased, and the seafloor community was dominated by organisms tolerant of lower oxygen conditions. The interaction between surface productivity and the deep seafloor was mediated by a continuous rain of organic material, dead organisms, fecal matter, and marine snow that settled downward through the water column. This biological pump transferred energy fixed by photosynthesis in surface waters to the deeper ocean, sustaining benthic communities that had no direct access to sunlight. The efficiency of this transfer varied with the depth of the water column and the rate of organic decomposition during descent, but in the shallow epicontinental seas of the Late Cretaceous, where depths rarely exceeded several hundred meters, the connection between surface productivity and seafloor communities was relatively direct and efficient. Fish diversity in late Cretaceous seas was considerable. Beyond the large predatory forms such as Zygphactinus, the oceans supported a broad spectrum of fish body sizes and feeding strategies. Teleost fish, the group that dominates modern ocean fish communities, were diversifying rapidly during the Cretaceous, and many of the ecological roles now occupied by modern marine fish were already represented in late Cretaceous faunas. Small schooling fish fed on plankton in surface waters, mid-sized predatory fish pursued them through the water column, and bottom-dwelling forms exploited the invertebrate communities of the seafloor. This diversity of fish life provided the caloric foundation that sustained the larger predators above them in the food web. The seasonal and geographic variation in marine productivity created corresponding patterns in predator distribution and behavior. In regions of high productivity upwelling zones, river mouths, and shallow coastal areas, prey was abundant and predator densities were correspondingly higher. In deeper or less productive open ocean environments, prey was more dispersed and predators necessarily more wide-ranging in their movements. Evidence from the isotopic composition of mosasaur and plesiosaur teeth suggests that some individuals ranged across considerable distances during their lifetimes, consistent with movement between productive feeding areas. The marine ecosystem of the Late Cretaceous had, by the final stages of the period, reached a state of ecological maturity comparable in complexity to modern ocean systems. Its food web extended from microscopic photosynthetic organisms at the base through successive layers of increasing body size and decreasing abundance, terminating in the large marine reptiles that cruise the surface and midwater zones of the ancient seas. Each level of this system was dependent on the functioning of those below it, and the stability of the whole rested on the continued productivity of the ocean's photosynthetic base, a productivity sustained, in turn, by the chemical and physical conditions of a warm, nutrient-rich, and largely ice-free ocean world. The most visible animals of the Late Cretaceous were those of substantial body size, the large herbivores moving across floodplains, the apex predators that pursued them, the enormous marine reptiles cruising shallow inland seas. But the biological complexity of the Cretaceous world was not concentrated in its largest inhabitants. At ground level, beneath the canopy of conifer forests and within the dense undergrowth of flowering plant communities, an entirely different set of organisms occupied the spaces between the giants, smaller, less conspicuous, and in many respects more ecologically diverse than the animals that have historically dominated reconstructions of the Mesozoic world. The forest floor of the Late Cretaceous was a structurally complex environment. Fallen logs in various stages of decomposition provided substrate for fungi, invertebrates, and the small vertebrates that fed on them. Leaf litter accumulated in layers, retaining moisture and supporting communities of detritivores, organisms that consumed dead organic material and, in doing so, released nutrients back into the soil. Root systems of trees and shrubs created a three-dimensional underground architecture that influenced soil structure, water retention, and the movement of small burrowing animals. The physical complexity of this environment at the centimeter and meter scale was, in many respects, greater than that of the open floodplains above it, and it sustained a corresponding diversity of life. Among the most ecologically significant inhabitants of the Cretaceous forest floor were the early mammals. Mammals had been present throughout the Mesozoic era, having diverged from their synodont ancestors during the Triassic period more than 200 million years ago. For most of that time, they had remained small, constrained, it is generally hypothesized, by the ecological dominance of dinosaurs in the large-bodied vertebrate niches. By the Late Cretaceous, mammals were represented by a diverse array of lineages, most of them small-bodied, with body masses typically ranging from a few grams to approximately 1 kilogram. A small number of Late Cretaceous mammal species may have reached body masses of several kilograms, but these were exceptions rather than the rule. Despite their small size, Late Cretaceous mammals exhibited considerable ecological diversity. Multituberculates, a group named for the multiple cusps arranged in rows on their molar teeth, were among the most abundant and widespread mammals of the period. Their dental morphology suggests a diet that included seeds, nuts, and other hard plant material, and their skeletal anatomy in some species indicates adaptations for climbing, consistent with an arboreal or semi-arboreal lifestyle. Marsupial relatives and early placental mammals were also present, though the precise relationships between these lineages and their modern descendants remain subjects of active paleontological research. Insectivorous forms with sharp, pointed teeth were common, and some lineages show skeletal features consistent with burrowing or semi-aquatic habits, suggesting that mammals had already diversified into a range of microhabitat niches by the final stages of the Cretaceous. The sensory biology of these early mammals reflects adaptations suited to a world in which avoiding larger animals was a consistent, selective pressure. Endocranial evidence indicates that Late Cretaceous mammals possessed relatively large brains for their body size compared to contemporary reptiles, with expanded regions associated with olfactory processing and auditory discrimination. Their hearing range extended to higher frequencies than those detectable by most reptiles, facilitated by the three-bone middle ear structure that distinguishes mammals from other vertebrates. These sensory capabilities would have been advantageous in low-light conditions at night, in dense vegetation, or in underground environments where visual information was limited and chemical and acoustic signals carried greater importance. Lizards were another significant component of the forest floor fauna. Squamates, the group that includes lizards and snakes, were diversifying rapidly during the Cretaceous, and by the Late Cretaceous, a wide range of lizard body forms and ecological strategies were represented in fossil faunas from North America, Asia, and Europe. Small insectivorous lizards occupied the ground layer and low vegetation, while larger forms fed on a broader range of prey, including small vertebrates and plant material. The fossil record of Cretaceous lizards is less complete than that of many other vertebrate groups, partly because their small, lightly built skeletons are less resistant to the taphonomic processes that determine what is preserved, but the diversity that is represented suggests a ground-level vertebrate community of considerable richness. Snakes also appear in the Cretaceous fossil record, though their diversity at this time was lower than it would become in subsequent periods. The earliest snake lineages were likely associated with aquatic or burrowing environments, and by the Late Cretaceous, several snake species are known from fragmentary remains in multiple continental regions. Their ecological role in Cretaceous ecosystems was probably as predators of small vertebrates and invertebrates, consistent with the feeding strategies of basal snake lineages inferred from comparative anatomy. The invertebrate community of the Cretaceous forest floor was both diverse and ecologically foundational. Insects, which had been diversifying since the Carboniferous period more than 300 million years earlier, were represented by a wide range of orders by the Late Cretaceous. Beetles, flies, wasps, ants, and moths are all documented from Cretaceous deposits, with many specimens preserved in amber fossilized tree resin that captures organisms with exceptional anatomical fidelity. Amber deposits from Burma, France, New Jersey, and other locations have yielded thousands of Cretaceous insect specimens, providing detailed information about the morphology and, in some cases, the behavior of these animals. Social insects, including early ants and some bee lineages, were present by the Late Cretaceous, and their ecological roles in soil aeration, decomposition, and plant pollination were already established components of terrestrial ecosystem function. Decomposition at the forest floor level was driven largely by fungi and invertebrates working in combination. Wood-boring beetles and other insects broke down fallen timber, increasing surface area for fungal colonization and accelerating the release of carbon and nutrients locked within woody tissue. Millipedes, mites, and springtails processed leaf litter and soil organic matter. Earthworm-like organisms contributed to soil mixing and aeration. This decomposer community, though rarely the focus of paleontological reconstruction, was essential to the nutrient cycling that sustained the plant communities above it and, by extension, the entire terrestrial food web. Frogs and salamanders were present in late Cretaceous freshwater and forest edge environments. Amphibians require moist conditions for reproduction, and the warm, humid climate of the late Cretaceous provided suitable habitat across a wide geographic range. Fossil frogs from this period show body plans broadly similar to modern forms, suggesting that the basic frog body plan had already been established and refined by this time. Their role as consumers of invertebrates and as prey for small reptiles and mammals placed them at an intermediate level of the food web, connecting the invertebrate community below to the small vertebrate community above. The ecological structure of the Cretaceous forest floor was therefore one of considerable biological layering. Decomposers processed dead organic material and returned nutrients to the soil. Invertebrates consumed plant material, fungi, and one another at multiple trophic levels. Small vertebrates, mammals, lizards, frogs, and early snakes fed on invertebrates and on each other, while simultaneously serving as prey for larger animals moving through or into the forest environment. Each of these interactions was embedded in a physical environment defined by moisture, shade, and the continuous input of organic material from the vegetation above. This ground-level world operated largely independently of the movements of large dinosaurs, except where those movements impacted the physical structure of the environment through trampling, vegetation removal, or the deposition of organic material in the form of dung and carcasses. In those moments of intersection, the two scales of the Cretaceous world briefly connected before the large animals moved on and the forest floor returned to its own rhythm, slow, continuous, and largely invisible against the scale of the giants that moved above it. Beneath the movement of large animals and above the slow processes of the forest floor, the plant communities of the Late Cretaceous were themselves undergoing a transformation of considerable ecological significance. This transformation had been building across tens of millions of years, driven not by a single event, but by the gradual diversification of a plant group whose ecological success would eventually reshape the structure of terrestrial ecosystems across the planet. The angiosperms, the flowering plants, had first appeared in the fossil record during the early Cretaceous, approximately 130 million years ago. Their origins remain a subject of active research, and the precise ancestral lineage from which they diverged is not yet fully resolved. What the fossil record does establish clearly is the trajectory of their subsequent diversification, slow and geographically restricted in their earliest phases, then accelerating through the Middle Cretaceous, and by the Late Cretaceous representing a dominant component of plant communities across a wide range of environments and latitudes. The ecological success of angiosperms was not incidental. It was grounded in a set of reproductive and physiological innovations that distinguished them from the gymnosperms, the conifers, cycads, and related seed plants that had dominated terrestrial vegetation for much of the Mesozoic. The most significant of these innovations was the enclosed seed. In angiosperms, the ovule is enclosed within a carpel, a protective structure that develops into the fruit following fertilization. This enclosure provides physical protection to the developing seed, can facilitate dispersal by animals that consume the fruit, and allows for a degree of maternal provisioning of the seed that is not possible in gymnosperms. The result is a reproductive system of greater flexibility and, in many environments, greater efficiency than that of non-flowering seed plants. Equally significant was the flower itself. The flower is a structure specialized for reproduction, concentrating the male and female reproductive organs in a form that facilitates pollination, the transfer of pollen from the male organ of one plant to the female organ of another. In wind-pollinated plants, pollen is produced in large quantities and dispersed passively, with fertilization dependent on chance contact. In animal-pollinated angiosperms, the flower provides resources, nectar, pollen itself, or other rewards that attract specific animal visitors, and the morphology of the flower is often shaped by co-evolutionary relationships with those visitors. This targeted pollination system is considerably more efficient in terms of pollen expenditure than wind pollination, and it allows for effective reproduction even when individual plants of the same species are widely spaced across the landscape. The insects that served as pollinators were already diverse and abundant by the Late Cretaceous. Beetles, flies, and wasps had been present since well before the appearance of angiosperms, and evidence from amber deposits and floral morphology suggests that these groups were among the earliest animal pollinators of flowering plants. Bees, whose morphology is highly specialized for pollen collection and transport, appear in the fossil record during the Cretaceous, and their diversification tracks closely with the diversification of angiosperms in ways consistent with a coevolutionary relationship. Moths and butterflies were also present by the Late Cretaceous, and their long feeding structures adapted for accessing nectar from tubular or deep-throated flowers indicate that specialized plant-pollinator relationships had already developed by this time. The physical structure of angiosperm-dominated vegetation differed from that of gymnosperm-dominated forests in ways that had direct consequences for the animals living within and around it. Angiosperms in many lineages grow more rapidly than gymnosperms under favorable conditions, and they respond more quickly to disturbance colonizing gaps created by fallen trees, flood events, or herbivore damage with greater speed than slower-growing conifers. This dynamic quality made angiosperm-dominated plant communities more structurally variable over time, creating a mosaic of vegetation ages and densities that supported a corresponding diversity of animal microhabitats. The leaves of many angiosperm species are broader and more nutritious than those of conifers, with higher concentrations of nitrogen and lower concentrations of secondary chemical compounds that deter feeding. This nutritional quality made angiosperm foliage more accessible as a food source for a wider range of herbivores than gymnosperm foliage, which tends to be resinous, tough, and chemically defended. The expansion of angiosperms across the Late Cretaceous landscape therefore represented not only a change in plant community composition, but a change in the nutritional landscape available to herbivorous animals. Hadrosaurs and other large herbivores were well positioned to exploit this expanding resource. Their dental batteries, capable of processing a wide range of plant material, would have been equally effective on angiosperm foliage as on the gymnosperms and ferns that had previously dominated their diet. Evidence from isotopic analysis of herbivore teeth and from the plant material preserved in association with herbivore remains suggests that large dinosaurs did consume angiosperm material, though the relative proportion of angiosperms versus other plant types in their diets varied by species, region, and the local availability of different vegetation types. Smaller herbivores and omnivores responded to the angiosperm expansion in ways that reflected their more specialized feeding strategies. The development of fruits as dispersal structures created a food resource that had not previously existed in terrestrial ecosystems, energy-rich, digestible packages that could sustain small mammals, birds, lizards, and insects. Animals that consumed fruits and subsequently deposited the seeds elsewhere through their digestive systems became agents of seed dispersal, extending the geographic reach of angiosperm populations and accelerating their colonization of new environments. This mutualistic relationship between fruiting plants and fruit-consuming animals was a genuinely novel ecological interaction in the Late Cretaceous, one that would become a defining feature of terrestrial ecosystems in subsequent geological periods. The coevolution between angiosperms and animals extended beyond pollination and seed dispersal. Plant defenses, chemical compounds produced to deter herbivory, diversified alongside the herbivores that fed on them, producing an escalating interaction between plant chemistry and animal digestive physiology that drove diversification in both groups. Some animal lineages evolved tolerance or detoxification mechanisms for specific plant compounds, allowing them to exploit resources unavailable to other herbivores. Plants whose chemical defenses were effective against most herbivores gained a competitive advantage in environments where herbivory was intense. The net effect of these interactions across millions of years was an increase in both plant and animal diversity, as each group diversified in partial response to the other. By the final stages of the Cretaceous, angiosperms had not fully displaced gymnosperms from all environments. Conifer-dominated forests persisted across many regions, particularly at higher latitudes and elevations where the competitive advantages of angiosperms were less pronounced. Ferns remained important components of ground-level vegetation, particularly in disturbed and moist environments. Cycads continued to occupy niches in warmer, drier settings. The Late Cretaceous plant community was therefore a mixed one, not yet the angiosperm-dominated world that would characterize the Cenozoic, but one in which the balance between plant groups had shifted substantially from the gymnosperm-dominated landscapes of the earlier Mesozoic. This transition in plant community composition was among the most consequential ecological changes of the Cretaceous period. It altered the nutritional content and physical structure of vegetation across broad areas, created new categories of plant-animal interaction that had not previously existed, and established the ecological foundations on which the biological communities of the subsequent era would be built. The flowering plants did not simply add diversity to an existing system. They gradually restructured the system itself, changing the rules of interaction between producers and consumers in ways that reverberated through every level of the terrestrial food web. The large animals of the Late Cretaceous did not occupy fixed positions within their landscapes. They moved across floodplains, through forest margins, along river corridors, and between environments that shifted seasonally in their productivity and resource availability. This movement was not random. It was structured by the biological requirements of large-bodied animals operating within ecosystems that varied across space and time, and it left traces in the fossil record that allow current researchers to reconstruct, with some confidence, the broad patterns of animal behavior and landscape use that characterize the period. The evidence for gregarious behavior among Late Cretaceous dinosaurs is substantial. Bone bed sites where the skeletal remains of multiple individuals are preserved in close association have been documented across several major fossil-bearing formations. In the Horseshoe Canyon and Two Medicine formations of Alberta, Canada, ceratopsian bone beds contain the disarticulated remains of dozens to hundreds of individuals of the same species, spanning a range of age classes from juveniles to fully grown adults. The depositional context of these sites, typically associated with river channel or floodplain sediments, suggests that groups of animals died together during events such as flooding, drought-related resource failure, or other environmental disruptions that affected multiple individuals simultaneously. The consistent species composition within individual bone beds and the presence of multiple age classes is broadly consistent with the interpretation that these animals moved in cohesive social groups rather than as solitary individuals that happened to congregate at a single location. Hadrosaur bone beds provide comparable evidence. Sites in Montana, Alaska, and several locations in Asia have yielded the remains of large numbers of hadrosaur individuals in single depositional units. The Pipestone Creek bone bed in Alberta, attributable to the hadrosaur Pachyrhinosaurus, contains an estimated minimum of 14 individuals, but likely represents a much larger original assemblage based on the density and distribution of skeletal material across the site. Isotopic analysis of hadrosaur bone material from high-latitude sites in Alaska has been used to investigate whether these animals undertook seasonal latitudinal migrations, moving northward during the productive Arctic summer and southward as light and temperature declined. Results from these analyses are not fully conclusive, but they are consistent with the hypothesis that some hadrosaur populations undertook substantial seasonal movements, potentially covering hundreds to over 1,000 kilometers annually. The geographic context of these potential migrations is relevant. The late Cretaceous landscape of western North America was structured by the presence of the western interior seaway to the east and a series of uplifting mountain ranges, the early ancestral Rocky Mountains to the west. Between these boundaries lay a broad lowland corridor of floodplains, river systems, and forested uplands that extended from the Gulf of Mexico northward into what is now Alaska. This corridor provided a continuous pathway along which large animals could move latitudinally, following the seasonal progression of vegetation productivity as temperatures and day lengths changed across the year. Seasonal variation in the late Cretaceous, while less extreme than in the modern world due to the reduced equator-to-pole temperature gradient, was not absent. High-latitude regions experienced substantial variation in day length across the year, producing seasonal differences in plant productivity even under a generally warm climate. Growth rings preserved in fossil wood from high-latitude Cretaceous deposits confirm that trees in these regions experienced seasonal interruptions in growth, consistent with periods of reduced light availability rather than cold temperatures. For large herbivores dependent on high volumes of plant material, these seasonal fluctuations in productivity would have created predictable patterns of resource abundance and scarcity that movement could partially mitigate. The mechanics of large-scale animal movement in the late Cretaceous were constrained by the same energetic principles that govern animal locomotion today. Larger animals require more absolute energy to move, but are generally more efficient per unit of body mass over long distances than smaller animals, due to the biomechanical advantages of larger stride length and lower mass-specific locomotion costs. For hadrosaurs and ceratopsians in the multi-ton body mass range, sustained long-distance movement was energetically feasible, provided that food and water were available at sufficient intervals along the route. Trackway evidence provides a complementary line of information about dinosaur movement patterns. Fossil trackways preserved in sedimentary rock, as the impressions left by animals walking across soft substrate, have been documented from numerous late Cretaceous localities. Some trackway sites record the movements of multiple individuals moving in the same direction simultaneously, consistent with gregarious movement across a landscape. The orientation of trackways relative to paleoenvironmental indicators, such as ancient river channels and vegetation boundaries, allows researchers to infer the directions of movement and the types of environments preferentially used or avoided by different animal groups. Predator behavior was also influenced by the movement patterns of large herbivore groups. In modern ecosystems, large predators often follow or anticipate the movements of migratory prey, concentrating their activity in areas and at times when prey is most accessible. There is no direct behavioral evidence for this pattern in the Cretaceous fossil record, but the spatial association between predator and prey remains in fossil-bearing formations is broadly consistent with predators occupying the same landscape corridors as their prey. Tyrannosaur remains are consistently found in the same formations and sedimentary environments as hadrosaur and ceratopsian remains, suggesting shared habitat use across the landscape. Nesting behavior introduced a different temporal structure to the annual cycles of large dinosaurs. Nesting sites, by their nature, require that animals return to specific locations at predictable times of year, introducing a degree of site fidelity into otherwise mobile lifestyles. Hadrosaur nesting sites documented in the Two Medicine Formation of Montana show evidence of repeated use across multiple seasons, with egg clutches and juvenile remains concentrated in specific areas that were returned to year after year. This pattern of nesting site fidelity, combined with evidence for juvenile growth within nesting areas before dispersal, suggests that the annual cycle of at least some hadrosaur populations was structured around a return to specific nesting localities, a behavioral constraint that would have shaped the broader movement patterns of those populations. Throughout the year, the survival strategies of large Late Cretaceous animals were therefore not simply a matter of individual responses to immediate conditions. They were expressions of behavioral patterns that had evolved over millions of years in response to the predictable seasonal and geographic structure of the Cretaceous landscape. Group movement buffered individuals against predation risk. Seasonal migration tracked the shifting geography of plant productivity. Nesting site fidelity concentrated reproductive effort in locations that had proven suitable across multiple generations. These behaviors were integrated with one another and with the physical environment in ways that reflect the long coevolution of animal communities and the landscapes they inhabited, a coevolution that had, by the final stages of the Cretaceous, produced animal societies of considerable behavioral complexity operating within ecosystems of corresponding ecological depth. The land surface and the seas of the Late Cretaceous were not the only biological domains of consequence. Above the forest canopy and across the open coastal margins, the air itself was occupied by animals whose evolutionary histories stretched back across tens of millions of years and whose ecological roles connected the aerial environment to the terrestrial and marine systems below. Two distinct groups dominated the skies of the Late Cretaceous. The pterosaurs, which had first appeared during the Triassic period approximately 228 million years ago, were by the final stages of the Cretaceous represented by some of the largest flying animals in the history of life on Earth. Alongside them, the birds whose lineage had diverged from small feathered theropod dinosaurs during the late Jurassic were diversifying rapidly, filling ecological roles across a wide range of body sizes and environments. Pterosaurs were not dinosaurs, though they shared a common archosaur ancestor and existed alongside dinosaurs throughout the Mesozoic. Their flight membranes, the patagia, stretched from an enormously elongated fourth finger on each hand to the body and hind limbs, forming a wing structure fundamentally different in architecture from that of birds or bats. This wing design, combined with hollow pneumatized bones that reduced skeletal mass, allowed pterosaurs to achieve body sizes in flight that have not been equaled by any other flying animal before or since. The largest pterosaurs known from the fossil record belong to the family Azhdarchidae, and their maximum body sizes represent an extreme of biological engineering whose precise aerodynamic mechanisms continue to be investigated. Quetzalcoatlus northropi, recovered from the Javelina Formation of Texas and dating to the latest Cretaceous, had an estimated wingspan of approximately 10 to 11 meters, comparable to the wingspan of a small modern aircraft. Body mass estimates for animals of this size are uncertain and dependent on assumptions about soft tissue distribution and bone density, but current figures generally range between 200 and 250 kilograms. At this body mass and wingspan, Quetzalcoatlus would have been capable of sustained soaring flight using thermal updraft, with metabolic costs during flight partially offset by the efficiency of soaring locomotion relative to powered flapping. The feeding ecology of large Azhdarchid pterosaurs has been the subject of considerable discussion. Early reconstructions depicted them as skim feeders flying low over water surfaces and dragging the lower jaw through the water to catch fish. Subsequent biomechanical analysis demonstrated that the jaw and neck structure of Azhdarchids was inconsistent with this feeding strategy, as the stresses generated by skim feeding at the body sizes involved would likely have exceeded the structural limits of the skull. Current interpretations favor a terrestrial stalking strategy in which large asdarchids walked on all four limbs across open landscapes and used their long necks and pointed jaws to seize prey from the ground, small vertebrates, invertebrates, and eggs in a manner broadly analogous to the foraging behavior of modern large wading birds such as storks. Trackway evidence attributed to asdarchid pterosaurs shows that these animals were competent quadrupedal walkers on land, supporting the interpretation that terrestrial foraging was a significant component of their ecology. Smaller pterosaur species occupied different ecological niches within the aerial environment. Fish-eating pterosaurs with elongated jaws and conical teeth were present in coastal and marine environments, plunging or wading to capture fish near the water surface. Some lineages possessed cranial crests of bone or soft tissue whose function likely encompassed display and species recognition. The diversity of pterosaur body forms and dental morphologies across the Cretaceous reflects a long history of ecological differentiation within the group, though by the latest, Cretaceous pterosaur diversity had declined relative to earlier periods, with the asdarchids becoming the dominant surviving lineage. The birds of the Late Cretaceous were a more diverse group than is sometimes recognized, though their diversity was substantially lower than that of modern avifauna. The earliest birds, represented by Archaeopteryx from the late Jurassic approximately 150 million years ago, retained many skeletal features of their theropod ancestors' teeth, clawed fingers, and a long, bony tail. By the Late Cretaceous, bird evolution had proceeded considerably further, and several distinct lineages had developed, some retaining teeth and others having lost them in favor of a keratinous beak. The Enantiornithes, the opposite birds, named for a distinctive feature of their shoulder joint anatomy, were among the most diverse and abundant bird groups of the Cretaceous. They ranged in body size from sparrow-like forms to animals approaching the size of a modern crow, and their foot morphology suggests that many were adapted for perching in trees and shrubs, with others showing adaptations for wading or ground foraging. Enantiornithine fossils have been recovered from sites across Asia, Europe, North America, and South America, confirming that this group had achieved a nearly global distribution by the Late Cretaceous. Despite their abundance and diversity during the Mesozoic, the Enantiornithines did not survive into the Cenozoic. Their extinction at the end of the Cretaceous removed what had been, by species count, the dominant bird group of the Mesozoic world. The ornithurin birds, the lineage that includes all modern birds, were also present during the Late Cretaceous, though in lower diversity than the Enantiornithines. Hesperornithiforms were a distinctive ornithurin lineage that had become secondarily flightless and fully aquatic, retaining teeth and developing powerful hind limbs for underwater propulsion in a manner convergent with modern diving birds such as loons. Ichthyornithiforms retained flight capability and possessed toothed jaws, and their skeletal morphology places them close to the base of the lineage that would give rise to modern birds. The presence of these early ornithurins in late Cretaceous deposits establishes that the ancestors of modern bird diversity were already present and differentiating before the end of the Mesozoic. The atmospheric conditions of the late Cretaceous influenced the physical environment through which flying animals moved. The elevated temperatures and higher water vapor content of the atmosphere affected air density and thermal dynamics in ways relevant to soaring flight. Warmer air generates stronger and more frequent thermal updrafts over heated land surfaces, and the broad, flat floodplains and coastal margins of the late Cretaceous would have produced reliable thermal columns during daylight hours. For large, soaring pterosaurs, these conditions would have been favorable, reducing the energetic cost of sustained aerial movement and extending the range over which individuals could travel without resorting to energetically expensive powered flapping. Wind patterns in the late Cretaceous atmosphere were influenced by the configuration of the continents, the extent of the inland seas, and the reduced temperature gradient between equatorial and polar regions. The absence of strong polar cooling reduced the intensity of the pressure gradients that drive mid-latitude westerly wind systems in the modern atmosphere, producing a circulation pattern that was, in some respects, calmer and more uniform than today. For flying animals operating at the scale of individual foraging ranges, local topographic and thermal effects would have been more immediately relevant than large-scale atmospheric circulation, but the broader atmospheric context determined the baseline conditions within which these local effects operated. The aerial fauna of the late Cretaceous was therefore a biologically and ecologically layered community, large soaring pterosaurs moving across open landscapes and coastal margins at altitude, smaller pterosaurs exploiting fish and invertebrates near water surfaces, enantiornithine birds diversified across forest and shrubland perching niches, and early ornithurans beginning the ecological diversification that would, in later geological periods, produce the extraordinary range of avian body forms and lifestyles present in the modern world. These animals connected the aerial environment to the ecosystems below as predators of terrestrial and aquatic prey, as seed dispersers and pollinators in some cases, and as prey themselves for larger aerial and terrestrial hunters. The sky of the late Cretaceous was not empty space above a living world. It was an inhabited dimension of that world, integrated into its ecological structure in ways that extended the biological complexity of the Cretaceous far above the ground on which its most famous animals walked. By the final stages of the late Cretaceous, the biological systems of the planet had reached a degree of integration and complexity that represented the cumulative product of hundreds of millions of years of evolutionary history. No single ecosystem, no individual species, and no isolated process can fully convey the scale of what the living world had become by this point. It was a planet in which life had colonized virtually every available environment, from the deepest accessible marine sediments to the upper reaches of the forest canopy, from the warm, shallow coastal seas to the high-latitude forests that persisted under the extended daylight of polar summers. The concept of biodiversity, as applied to the late Cretaceous, encompasses more than a simple count of species. It refers to the functional variety of organisms within ecosystems, the range of ecological roles occupied, the diversity of physiological strategies employed, and the complexity of interactions between species that collectively determined how energy and materials move through biological communities. By each of these measures, the late Cretaceous biosphere was extraordinarily rich. On land, the layered structure of terrestrial ecosystems distributed biological activity across multiple vertical zones. The forest canopy intercepted the majority of incoming solar radiation, supporting photosynthetic production that sustained the entire system below. Beneath the canopy, an understory of smaller trees and shrubs occupied intermediate light levels, filtering the radiation that passed through and creating a gradient of light intensity that extended down to the forest floor. At ground level, ferns, mosses, and low-growing angiosperms exploited the diffuse light that reached the soil surface, while fungi and decomposer invertebrates processed the organic material that fell continuously from above. Each of these vertical zones supported its own community of animals. The canopy was inhabited by insects, early birds, and small climbing vertebrates. The understory provided perching and nesting habitat for smaller flying animals and foraging space for medium-sized terrestrial vertebrates moving through the forest interior. The ground layer was occupied by the diverse community of small mammals, lizards, frogs, snakes, and invertebrates whose ecological roles have been described in earlier segments of this account. And below the ground surface, the soil fauna, nematodes, mites, earthworm-like organisms, burrowing insects, and early burrowing mammals processed organic material and cycled nutrients in ways that sustained the plant communities above. The horizontal structure of late Cretaceous landscapes added another dimension to this biological complexity. Ecosystems were not uniform across the landscape, but varied continuously with topography, hydrology, and soil characteristics. River floodplains supported distinct plant and animal communities from the upland forests and shrublands adjacent to them. Coastal margins where terrestrial and marine systems met were zones of particularly high productivity and biological diversity, where nutrients delivered by river systems supported dense communities of both aquatic and terrestrial organisms. Freshwater lakes and wetlands provided habitat for specialized communities of aquatic invertebrates, fish, amphibians, and the reptiles and early birds that fed on them. The marine realm contributed an entirely separate dimension of biodiversity. The shallow epicontinental seas were among the most productive marine environments of the period, supporting food webs that extended from microscopic photosynthetic plankton through invertebrates, fish, and cephalopods to the large marine reptiles at the apex. The open ocean supported different but equally complex communities, structured by the vertical gradient of light penetration and the horizontal variation in nutrient availability between productive coastal upwelling zones and the relatively nutrient-poor central ocean gyres. The interactions between these ecosystems were mediated by the movement of organisms, materials, and energy across their boundaries. Rivers carried organic material and nutrients from terrestrial systems into coastal and marine environments. Marine-derived nutrients were transported inland by animals that fed in the sea and moved onto land, a process documented in modern ecosystems through the movement of anadromous fish and the animals that prey on them, and likely operating in analogous forms in the Cretaceous world. Flying animals crossed ecosystem boundaries routinely, feeding in one environment and depositing nutrients in another through their waste. The boundaries between ecosystems were therefore not barriers but zones of exchange that connected otherwise distinct biological communities into a larger, integrated biosphere. The microbial foundation of this biosphere was ancient, pervasive, and essential. Bacteria and archaea occupied every environment accessible to life soils, water columns, sediments, and the bodies of larger organisms. Microbial communities in soils drove the decomposition and nutrient cycling that sustained plant productivity. Marine microbes fixed nitrogen, processed sulfur compounds, and contributed to the chemical cycling of carbon between the ocean, atmosphere, and sediment. The metabolic activities of microbial communities were, in aggregate, responsible for transformations of matter and energy at a scale that dwarfed the contributions of any individual macroscopic organism or group of organisms, however large or ecologically prominent. The evolutionary processes that had produced this biological complexity were still operating throughout the late Cretaceous. Species were not static entities, but populations in continuous genetic change, responding to the selective pressures imposed by their physical environments and by the other organisms with which they interacted. Speciation, the divergence of populations into reproductively isolated lineages, was proceeding across all groups of organisms, adding new species to existing communities while extinction removed others. The net rate of speciation relative to extinction during the Late Cretaceous was, across most groups, sufficient to maintain or gradually increase biological diversity consistent with a biosphere that was, in broad terms, ecologically stable and biologically productive. The physical conditions that sustained this biological richness were themselves the product of long-term geological and atmospheric processes. The warm climate was maintained by elevated greenhouse gas concentrations, sustained by volcanic outgassing, and modulated by the slow chemical weathering of rocks. The distribution of land and sea, shaped by plate tectonics operating across hundreds of millions of years, determined the circulation of ocean currents and the movement of atmospheric moisture in ways that influenced precipitation and temperature patterns across the globe. The chemical composition of the ocean, its salinity, pH, and nutrient content reflected the balance between inputs from rivers and volcanic sources and outputs through biological uptake and sediment burial. These physical systems operated across timescales that dwarfed the lifespan of any individual organism or even of any individual species. The biological communities of the Late Cretaceous were, in a sense, passengers within a much larger Earth system sustained by physical conditions that had developed over geological time and that would, given sufficient time and the absence of disruptive perturbations, continue to evolve slowly and predictably. The ecosystems of the period were adapted to those conditions, calibrated by millions of years of evolutionary response to the specific temperature, chemistry, and geography of the Late Cretaceous Earth. It was a world of extraordinary biological completeness, not perfect or unchanging, but functional, integrated, and rich in ways that reflected the full depth of evolutionary time from which it had emerged. The diversity of life in the Late Cretaceous was not an accident or an anomaly. It was the expected outcome of a planet with stable physical conditions, abundant energy from the sun, liquid water across most of its surface, and hundreds of millions of years of uninterrupted biological evolution. By every measure available to current science, it was one of the most biologically elaborate states the Earth had ever achieved. The biological richness of the Late Cretaceous did not persist without variation. Beneath the apparent stability of its ecosystems, detectable changes were accumulating across multiple timescales, some unfolding over millions of years, others compressed into intervals of tens or hundreds of thousands of years. These changes were not, in themselves, unprecedented. Ecosystems across Earth's history have absorbed and responded to environmental fluctuations of considerable magnitude. What distinguished the changes occurring in the final stages of the Cretaceous was not their individual severity, but their convergence, the way in which multiple independent processes began to exert simultaneous pressure on biological systems that had been calibrated to a specific set of physical conditions. The most significant geological process operating during the latest Cretaceous was the intensifying volcanic activity of the Deccan Traps. This large igneous province, located in what is now the western Deccan Plateau of India, was producing lava flows of extraordinary volume across a period that spans the final few 100,000 years of the Cretaceous and extends into the earliest Paleogene. The total volume of basaltic lava erupted by the Deccan Traps over its full active period is estimated at approximately 1 to 1.5 million cubic kilometers, sufficient, if spread evenly, to cover the entire surface of the modern continental United States to a depth of roughly 150 meters. This material did not erupt instantaneously, but was delivered in a series of pulses separated by intervals of relative quiescence, with the most voluminous phase of eruption coinciding broadly with the final stages of the Cretaceous period. The biological consequences of large igneous province volcanism operate through several mechanisms. The most immediate is the release of sulfur dioxide gas, which reacts with water vapor in the atmosphere to form sulfate aerosols. These aerosols reflect incoming solar radiation, producing short-term surface cooling that can persist for years to decades following major eruptive episodes. The cooling effect of sulfate aerosols is real, but temporary aerosols are removed from the atmosphere through precipitation within a few years, and the longer-term thermal effect of the associated carbon dioxide release is one of warming rather than cooling. The interplay between these two mechanisms, short-term sulfate cooling and longer-term CO2 warming, produces a complex pattern of environmental perturbation that varies in its biological impact depending on the duration and intensity of individual eruptive pulses. Evidence for biological stress associated with Deccan volcanism has been identified in several fossil records from the latest Cretaceous. Marine microfossil assemblages, particularly the shells of foraminifera, single-celled marine organisms whose chemical composition reflects the temperature and chemistry of the water in which they lived, show fluctuations in the final hundreds of thousands of years of the Cretaceous consistent with episodes of environmental instability. Some studies of terrestrial plant communities from this interval have identified shifts in vegetation composition that may reflect responses to changing temperature or precipitation patterns. The interpretation of these records is complicated by the difficulty of distinguishing volcanic signals from background ecological variability, and scientific opinion on the magnitude of pre-extinction biological stress attributable to Deccan volcanism remains divided. Marine ecosystems show additional evidence of change during the latest Cretaceous. Ammonite diversity, which had already been declining through much of the late Cretaceous, continued to decrease in the final stages of the period. Some lineages that had been widespread earlier in the Cretaceous had disappeared or become restricted in geographic range by the Maastrichtian stage, the final stage of the Cretaceous, spanning from approximately 72 to 66 million years ago. Whether this decline reflects a genuine long-term trend driven by environmental change or represents normal background extinction rates within a diverse group is a question that continues to be examined as the resolution of the fossil record improves. On land, the dinosaur fossil record of the latest Cretaceous has been analyzed for evidence of diversity trends in the interval preceding the extinction. Studies of the Hell Creek Formation in western North America, one of the most thoroughly sampled latest Cretaceous terrestrial fossil records available, have produced conflicting results. Some analyses identify a decline in dinosaur species diversity in the final million years before the extinction boundary, while others argue that apparent diversity declines reflect sampling artifacts, the uneven distribution of fossil collecting effort across the formation rather than genuine biological trends. Resolving this question requires continued expansion of the fossil record and increasingly sophisticated statistical approaches to account for sampling variation. Climate variability during the Maastrichtian added another layer of complexity to the environmental context of latest Cretaceous life. Isotopic records from marine sediments indicate that global temperatures fluctuated across this interval, with a general cooling trend interrupted by warmer episodes. Sea levels also varied, with evidence for regression, the withdrawal of shallow seas from continental interiors during parts of the Maastrichtian. In North America, the western interior seaway, which had divided the continent for much of the late Cretaceous, was retreating during the final stages of the period as sea levels fell and the seaway shallowed. This regression altered the geography of the continent, changing drainage patterns, modifying the distribution of coastal and lowland habitats, and potentially disrupting the connectivity between ecosystems that had previously been linked by the shallow marine corridor. The response of biological communities to these environmental fluctuations was mediated by the ecological properties of the organisms involved. Species with broad geographic ranges, generalist dietary strategies, and high reproductive rates were generally better positioned to absorb environmental variability than specialists with narrow ranges and specific resource requirements. The fossil record provides examples of both responses, lineages that maintain their diversity and distribution through the environmental fluctuations of the Maastrichtian, and others that show evidence of range, contraction, or diversity decline during this interval. It is important to maintain appropriate scientific caution when interpreting these patterns. The latest Cretaceous fossil record, however well sampled in some regions, is inevitably incomplete. The absence of a taxon from a particular stratigraphic interval does not necessarily indicate its extinction. It may reflect preservation bias, sampling gaps, or the movement of populations out of the area represented by the available rock record. The patterns identified in current analyses represent the best available interpretation of an inherently incomplete dataset, and they are subject to revision as new fossil material and new analytical methods become available. What the available evidence does support is the conclusion that the biological world of the latest Cretaceous was not perfectly static. It was a system experiencing measurable perturbations from volcanic forcing, climate variability, and sea level change perturbations that were producing detectable responses in at least some components of the biosphere. These changes were, by the standards of Earth's geological history, neither uniquely severe nor inherently catastrophic. They were the kind of environmental fluctuations that ecosystems had absorbed and responded to repeatedly across the deep history of life on this planet. The biological systems of the latest Cretaceous had the capacity, developed across millions of years of evolutionary history, to respond to change, to shift in composition, to reorganize ecologically, and to persist through intervals of environmental stress. That capacity was real, and it had been tested and confirmed repeatedly across the long history of life on Earth. What it had not been tested against was a perturbation of a fundamentally different order of magnitude, one that would arrive not gradually, but in geological terms, almost instantaneously. The environmental pressures accumulating during the latest Cretaceous were not confined to a single system. They operated simultaneously across the atmosphere, the ocean, and the land surface, and their combined effect was to introduce a degree of instability into biological communities that had been calibrated over millions of years to a relatively consistent set of physical conditions. The changes were not yet catastrophic, but they were measurable, and their effects on living systems were becoming increasingly apparent in the fossil and geochemical records that preserve the final stages of the Cretaceous world. The regression of shallow seas from continental interiors was among the most geographically significant changes of the Maastrichtian stage. As sea levels fell during the final millions of years of the Cretaceous, the epicontinental seas that had shaped the geography, climate, and ecology of the preceding period progressively withdrew. In North America, the retreat of the western interior seaway transformed the physical landscape of the continent in ways that had direct consequences for the biological communities living within and adjacent to it. The seaway had functioned as a moderating influence on regional climate, its thermal mass buffering, seasonal temperature extremes, and its evaporative surface contributing moisture to the surrounding lowlands. As it withdrew, the continental interior became more exposed to seasonal temperature variation, and the humid lowland environments that had persisted along its margins gave way to drier, more climatically variable conditions. The withdrawal of the seaway also altered drainage patterns across the continent. River systems that had previously discharged into the inland sea were reorganized as the basin they drained was progressively exposed and elevated by the tectonic activity associated with the early Rocky Mountain uplift. New river systems developed, and existing ones shifted their courses, redistributing sediment and altering the distribution of floodplain habitats across the landscape. These changes in hydrology affected the availability and distribution of the moist, productive lowland environments that had supported high densities of large herbivorous dinosaurs throughout the Late Cretaceous. The early uplift of the Rocky Mountain system, a process known as the Laramide orogeny, was proceeding during the Maastrichtian and was itself contributing to the environmental changes of this interval. Mountain building affects regional climate through multiple mechanisms. Elevated terrain intercepts atmospheric moisture, producing increased precipitation on windward slopes and rain shadow conditions on leeward sides. The physical barrier presented by an uplifting mountain range alters atmospheric circulation patterns, redirecting wind systems and modifying the distribution of precipitation across broad areas. As the ancestral Rocky Mountains rose during the latest Cretaceous, the landscapes to the east of the uplift experienced changes in precipitation patterns that contributed to the progressive drying of previously humid lowland environments. Volcanic forcing from the Deccan Traps continued to interact with these tectonic and climatic changes. The most voluminous phase of Deccan eruption is now understood, based on high-resolution geochronological dating, to have been concentrated in the interval immediately surrounding the end Cretaceous boundary, with substantial eruptive activity occurring both before and after the extinction event itself. The precise timing of individual eruptive pulses relative to the extinction boundary remains an area of active research, and the degree to which Deccan volcanism contributed to biological stress in the final stages of the Cretaceous, independent of other factors, is not yet fully resolved. What is established is that the atmospheric inputs from this volcanism, sulfur dioxide, carbon dioxide, and associated trace gases were being added to an atmosphere already experiencing variability from other sources, compounding the environmental perturbations experienced by biological communities during this interval. The chemical effects of elevated volcanic outgassing on the ocean were potentially significant. Increased atmospheric CO2 dissolves into seawater, producing carbonic acid and lowering ocean pH in a process known as ocean acidification. Organisms that build calcium carbonate shells or skeletons, including many marine invertebrates, corals, and the coccolithophore algae that form the base of the marine food web, are sensitive to changes in ocean carbonate chemistry, as acidification reduces the availability of carbonate ions needed for shell construction. Evidence for ocean acidification episodes during the latest Cretaceous has been identified in some geochemical records, though the magnitude and geographic extent of these episodes and their biological consequences are subjects of continuing investigation. On land, the response of plant communities to the changing environmental conditions of the Maastrichtian provides another window into the ecological dynamics of this interval. Palynological records, the fossil record of pollen and spores preserved in sedimentary sequences from latest Cretaceous deposits in several regions, show shifts in plant community composition that are broadly consistent with responses to changing temperature and moisture regimes. In some sequences, changes in the relative abundance of different pollen types suggest a shift toward plant communities adapted to drier or more seasonally variable conditions. In others, the pollen record shows relatively little change until the extinction boundary itself, suggesting that plant communities in those regions were more resilient to the environmental fluctuations of the Maastrichtian or that those regions were less directly affected by the changes underway elsewhere. The animal communities of the latest Cretaceous were embedded within these changing plant communities and were therefore indirectly affected by shifts in vegetation structure and composition. Large herbivores dependent on specific types of vegetation would have experienced changes in the availability and nutritional quality of their food resources as plant communities shifted. Predators dependent on specific prey species would have been affected by any changes in prey population density or distribution. The ecological interconnections that had developed across millions of years of coevolution meant that changes in any one component of the system had the potential to propagate through multiple trophic levels. The pace of these changes is critical to understanding their biological significance. Gradual environmental change, unfolding over thousands to millions of years, provides time for evolutionary and ecological responses for populations to shift their ranges, for communities to reorganize, for natural selection to favor individuals better suited to new conditions. The changes of the Maastrichtian, while real and measurable, were unfolding on timescales that, though geologically rapid in some respects, still allowed for biological response and adjustment. The fossil record of the latest Cretaceous does not present a picture of ecosystems in collapse. It presents a picture of ecosystems under stress, responding and adapting, maintaining their fundamental structure while absorbing perturbations at their margins. This distinction is significant. A world under stress is not the same as a world at the point of failure. The biological communities of the latest Cretaceous retain their basic ecological architecture, their trophic structure, their species diversity, their functional organization through the environmental fluctuations of the Maastrichtian. They were changed by those fluctuations, but not fundamentally disrupted. The capacity of these ecosystems to absorb change had been demonstrated repeatedly across the long history of the Cretaceous, and there was, in the pattern of environmental change observable in the Maastrichtian record, no indication that the threshold of that capacity was about to be reached. The changes accumulating in the physical world were real, and their biological effects were measurable. But they were, by the standards of Earth's geological history, within the range of what living systems had survived before. What was coming was not. The world of the latest Cretaceous, in the final thousands of years before the extinction boundary, retained the fundamental biological architecture that had characterized it across the preceding tens of millions of years. Dinosaurs still moved across its floodplains. Marine reptiles still cruised its shallow seas. Flying animals still occupied its skies. The ecosystems of this world were under measurable stress from the accumulating environmental pressures of the Maastrichtian, but they had not collapsed. Life, in its full late Cretaceous expression, persisted into the very final interval of the period, and the organisms that inhabited that interval were, in most respects, continuous with those that had inhabited the centuries and millennia before them. In western North America, the landscape of the latest Cretaceous was defined by the depositional environment now preserved as the uppermost Hell Creek Formation. This formation, laid down across what is now Montana, North Dakota, South Dakota, and Wyoming, represents one of the most thoroughly sampled latest Cretaceous terrestrial fossil records available to current science. Its sediments preserve a floodplain environment of low relief, crossed by river channels of varying size, interspersed with ponds, swamps, and areas of dense vegetation. The climate of this region during the latest Cretaceous was warm and seasonally variable, with mean annual temperatures estimated at approximately 10 to 15 degrees Celsius cooler than earlier in the Cretaceous due to the general Maastrichtian cooling trend, but still substantially warmer than the modern climate of the same geographic region. Within this environment, Tyrannosaurus rex was present as the apex predator. Current estimates of Tyrannosaurus population density, derived from the abundance of its remains relative to those of prey animals in Hell Creek deposits and from ecological scaling relationships between predator body size and population density, suggest that individual animals were widely spaced across the landscape, perhaps one individual per several tens of square kilometers of suitable habitat. Despite this low density, Tyrannosaurus remains are represented by dozens of individual specimens from Hell Creek deposits, spanning a range of growth stages from juveniles to fully mature adults, providing a detailed picture of the population structure of this species in the final interval of its existence. The prey community available to Tyrannosaurus in the latest Hell Creek environment included several hadrosaur species, among them Edmontosaurus annectens, a large, crestless hadrosaur that reached body lengths of approximately 9 to 12 meters and represented one of the most abundant large herbivores in the formation. Triceratops horridus was similarly abundant, its remains constituting a significant proportion of the large vertebrate fossil assemblage from uppermost Hell Creek deposits. The persistence of these prey species in high relative abundance through the final stratigraphic levels of the Hell Creek Formation indicates that the herbivore community of this environment remained functional and productive into the very latest Cretaceous. Alongside these larger animals, the Hell Creek fauna included a diverse assemblage of smaller vertebrates that had characterized the formation throughout its depositional history. Small ceratopsians, pachycephalosaurs, dome-headed dinosaurs whose thickened skull roofs are among the most distinctive anatomical features in the Late Cretaceous fossil record, and ornithomimosaurs contributed to the overall diversity of the dinosaur fauna. Lizards, early mammals, frogs, salamanders, turtles, and crocodilians occupied the lower levels of the terrestrial and freshwater ecosystems, their communities broadly continuous with those documented from earlier in the Cretaceous. The mammal fauna of the latest Hell Creek is of particular significance in retrospect, though nothing in the fossil record of these animals themselves would have distinguished the final Cretaceous interval from what preceded it. Multituberculates, marsupial relatives, and early placental mammals were present, their remains small and fragmentary, their ecological roles as insectivores, omnivores, and small herbivores unchanged from earlier stages of the formation. These animals were, at the moment of the extinction boundary, simply the latest expression of mammalian lineages that had been present throughout the Cretaceous small. Ecologically marginal by the standards of a world dominated by large dinosaurs, and entirely without any apparent indication in their biology or behavior of the role their descendants would come to play in the world that followed. Beyond North America, the latest Cretaceous fauna of other continental regions showed comparable patterns of continuity. In Asia, the Nemegt Formation of Mongolia preserves a diverse latest Cretaceous fauna that includes the Tyrannosaur tarbosaurus, large hadrosaurs including Saurolophus, the giant sauropod Opisthocoelocordia, ankylosaurs, and a diverse assemblage of smaller theropods. In Europe, the island archipelago faunas of the latest Cretaceous included dwarf sauropods animals whose reduced body size relative to their continental relatives reflects the ecological consequences of island isolation and resource limitation alongside ankylosaurs, small theropods, and diverse non-dinosaurian vertebrates. In South America, titanosaur sauropods and abelosaurid theropods persisted through to the extinction boundary, their communities distinct in composition from those of the Northern Hemisphere, but equivalent in ecological structure. The marine environments of the latest Cretaceous similarly retained their fundamental biological organization through the final interval of the period. Mosasaurs remained the dominant large marine predators, with several genera represented in latest Cretaceous marine deposits from multiple ocean basins. Plesiosaurs, though reduced in diversity relative to earlier periods, persisted into the final stages of the Cretaceous in both the long-necked elasmosaurid and short-necked polycotylid body forms. Sharks, large bony fish, and diverse invertebrate communities continued to populate the water column and seafloor of the shallow epicontinental seas and open ocean environments. The skies of the latest Cretaceous remained inhabited by pterosaurs and birds. Large azhdarchid pterosaurs, including Quetzalcoatlus, are documented from latest Cretaceous deposits, their presence confirmed by both skeletal remains and the trackway evidence of their terrestrial movements. Enantiornithine birds continued to occupy perching and foraging niches across forested environments, and ornithurin birds. The lineage ancestral to all modern avian diversity were present and diversifying in coastal and aquatic environments. In the plant communities of the latest Cretaceous, angiosperms continued their ecological expansion, maintaining the mixed vegetation structure that had characterized the period angiosperm-dominated in many lowland and disturbed environments, gymnosperm-dominated in upland and higher latitude settings. The palynological record from the very latest Cretaceous shows plant communities broadly continuous with those of the preceding Maastrichtian, with no dramatic reorganization of vegetation composition detectable in the stratigraphic interval immediately preceding the extinction boundary. What the fossil record of the latest Cretaceous presents, in aggregate, is a world still fully inhabited, still organized according to the ecological principles and trophic relationships that had defined it across tens of millions of years. The large dinosaurs that have come to represent this world in the scientific and cultural imagination were alive, feeding, moving, and reproducing in the final years, decades, and centuries before the extinction boundary. There is no evidence in the fossil record of a gradual cessation of dinosaur life, no progressive thinning of the fauna, no biological winding down that might have been visible to a hypothetical observer moving through the latest Cretaceous landscape. The world was alive. Its ecosystems were functioning. Its animals were present in the diversity and abundance that the latest Cretaceous environment could support. And then, in the context of geological time, something happened that was outside the range of anything this world, or any world that had existed in the preceding history of complex animal life on Earth, had previously experienced. It arrived not as a continuation of the changes already underway, but as a rupture. A discontinuity so abrupt, so energetically extreme, and so globally comprehensive in its effects that the geological boundary it produced is detectable in rock sequences on every continent and in every ocean basin on the planet. The Cretaceous did not fade. It ended. The geological boundary that marks the end of the Cretaceous period is preserved in rock sequences across the planet as a layer of material typically only a few centimeters thick. Within that layer, and in the sediments immediately above it, the fossil record undergoes a transformation of extraordinary abruptness. The organisms that had characterized late Cretaceous ecosystems, the large dinosaurs, the marine reptiles, the pterosaurs, the ammonites, the diverse communities of marine invertebrates, are absent. Not reduced in diversity, not restricted in range, but absent. The biological world documented in the sediments below the boundary does not continue into the sediments above it. What continues is something fundamentally different, a world in the process of being rebuilt from a severely diminished biological foundation. The physical agent of this transformation was the impact of an extraterrestrial body, an asteroid, estimated at approximately 10 to 15 kilometers in diameter, that struck the shallow marine platform of what is now the Yucatan Peninsula of Mexico approximately 66 million years ago. The energy released by this impact has been calculated at approximately 100 teratons of TNT equivalent, a value that exceeds the combined explosive yield of every nuclear weapon ever constructed by a factor of several billion. The impact produced a crater now known as Chicxulub, approximately 180 kilometers in diameter and 20 kilometers deep, whose subsurface structure has been mapped in detail through geophysical surveys and drilling programs conducted over several decades of scientific investigation. The immediate physical consequences of the impact unfolded across a sequence of timescales ranging from seconds to years. In the first seconds, the kinetic energy of the impactor was converted almost instantaneously into thermal energy, vaporizing the impactor itself and a substantial volume of the target rock, and generating a fireball of extreme temperature that radiated outward from the impact site. The vapor plume, a column of superheated rock and gas, was ejected into and beyond the upper atmosphere, with material reaching velocities sufficient to escape the gravitational pull of the lower atmosphere and follow ballistic trajectories before re-entering. As this ejector re-entered the atmosphere across a global distribution, the frictional heating generated by its passage through the upper atmosphere produced a brief but intense pulse of infrared radiation at the surface, a thermal event estimated to have lasted for approximately 1 to 2 hours at intensities sufficient to ignite surface vegetation across continental scale areas. The wildfires initiated by this thermal pulse are recorded in the geological boundary layer as elevated concentrations of soot and charcoal combustion products preserved in fine-grained sediments deposited in the immediate comprimer. Aftermath of the impact. The global distribution of this soot layer, identified in boundary sequences from multiple continents and ocean basins, confirms that fire was not a local phenomenon but a consequence operating at hemispheric to global scale. The combustion of surface vegetation removed a significant fraction of the terrestrial primary productivity that had sustained land-based food webs, and the soot and ash injected into the atmosphere by these fires contributed to the opacity of the post-impact atmosphere. The longer-term atmospheric consequences of the impact were driven primarily by the material ejected from the target rock itself. The Chicxulub impact site was underlain by thick deposits of sulfur-rich evaporite rock, gypsum, and anhydrite, whose vaporization released enormous quantities of sulfur dioxide into the upper atmosphere. Sulfur dioxide reacts with water vapor to form sulfate aerosols, which reflect incoming solar radiation and produce surface cooling. Estimates of the sulfur released by the Chicxulub impact, based on the volume and composition of the target rock, suggest that the resulting aerosol loading of the stratosphere was sufficient to reduce surface solar radiation to levels that impaired or effectively halted photosynthesis across broad areas of the planet for a period of months, potentially years. The cessation of photosynthesis was the mechanism through which the physical consequences of the impact translated into biological catastrophe. Terrestrial food webs depended at their base on the conversion of solar energy into biological matter by plants. Marine food webs depended on the equivalent process carried out by phytoplankton in surface waters. When light ceased to reach the surface in sufficient quantities to sustain photosynthesis, both of these foundational processes were interrupted. The effects propagated upward through the food web with a speed determined by the energy reserves of organisms at each trophic level and the rate at which those reserves were depleted in the absence of new primary production. In the ocean, the impact of the photosynthetic shutdown on marine ecosystems was rapid and severe. The calcareous nanoplankton, the coccolithophores, and related organisms that had formed the base of the marine food web and whose accumulated remains had built the chalk deposits of the Cretaceous seafloor experienced a collapse in diversity and abundance that is recorded with exceptional clarity in marine sediment sequences spanning the boundary. Above the boundary layer, the assemblage of nanoplankton species is drastically reduced, with the diverse Late Cretaceous community replaced initially by a depauperate assemblage of opportunistic forms. The recovery of nanoplankton diversity to pre-boundary levels required hundreds of thousands to millions of years, a timescale that reflects the depth of the ecological disruption at the base of the marine food web. The large marine reptiles did not survive. Mosasaurs and plesiosaurs, whose ecological success had been built on the productive marine ecosystems of the Late Cretaceous, disappear from the fossil record at the boundary. Their absence in post-boundary sediments is absolute. There are no surviving lineages, no populations that persisted through the ecological disruption of the immediate post-impact interval. The food web that had sustained them had been fundamentally disrupted at its base, and animals of their body size and metabolic requirements could not survive the interval of reduced marine productivity that followed. On land, the pattern of extinction was similarly structured by the disruption of primary productivity, but the specific outcomes varied among different groups of organisms in ways that reflect differences in body size, metabolic rate, dietary flexibility, and the ability to exploit energy sources that did not depend on living primary producers. Large animals with high metabolic requirements and specialized diets were most vulnerable. The non-avian dinosaurs, every lineage of large-bodied dinosaur that had characterized the Cretaceous terrestrial fauna, disappeared entirely. No large dinosaur is known from sediments deposited above the Cretaceous-Paleogene boundary. The extinctions were not gradual and were not preceded by a progressive decline detectable in the fossil record immediately below the boundary. They were abrupt, in geological terms, and total. The groups that survived the extinction event share a set of characteristics that, in retrospect, can be understood as conferring resilience under the specific conditions of the post-impact world. Small body size reduced absolute energetic requirements, allowing survival on limited food resources for longer periods. Dietary flexibility, the ability to consume a wide range of food types, including detritus, seeds, insects, and decaying organic matter, provided access to energy sources that persisted through the photosynthetic shutdown. Burrowing or aquatic habits provided physical shelter from the thermal pulse and access to food resources buffered from the immediate surface disruption. The early mammals survived. Their small body size, generalist diets, and likely nocturnal habit adaptations developed across tens of millions of years of existence as minor components of dinosaur-dominated ecosystems proved, under the radically altered conditions of the post-impact world, to be precisely the characteristics that allowed persistence through the extinction interval. The birds, specifically the ornithurin lineage, ancestral to all modern avian diversity, also survived, while the enantiornithines and all non-avian dinosaurs did not. Turtles, crocodilians, lizards, snakes, frogs, and salamanders persisted through the boundary in reduced diversity. Their relatively low metabolic requirements and dietary flexibility providing a degree of resilience that larger, more specialized animals did not possess. The world that existed in the years and decades immediately following the impact was not simply impoverished, it was functionally reorganized at its most basic level. The ecological roles that large dinosaurs had occupied for more than 160 million years were vacant. The marine niches held by mosasaurs and plesiosaurs were empty. The skies that pterosaurs had inhabited since the Triassic were now occupied only by the surviving birds. The trophic structure that had organized terrestrial and marine ecosystems across the entire Mesozoic era had been dismantled, not gradually, but in a geological instant, and what remained was a biological world reduced to its most resilient components, distributed across a physically altered planet still recovering from the atmospheric and climatic consequences of the impact itself. The silence that followed was not absolute. Life had not been eliminated. But the particular expression of life that the Earth had sustained across the Cretaceous, the specific assemblage of organisms, ecological relationships, and biological complexity that had developed across tens of millions of years of evolution, was gone. The floodplains that had carried the weight of multi-ton herbivores were empty of that weight. The shallow seas that had sustained the largest marine predators in the planet's history were quiet at their upper levels. The forests that had sheltered the most diverse small vertebrate communities of the Mesozoic still stood, in places, but the large animals that had moved through them and shaped them were absent. What persisted was a foundation stripped down, reduced, and ecologically simplified, but biologically continuous with what had come before. From that foundation, across the tens of millions of years that followed, the survivors would diversify, expand, and eventually rebuild a living world of comparable complexity to the one that had been lost. But that process belonged to a different era entirely. The Cretaceous was over. The age that had belonged to the dinosaurs had ended not with a gradual transition, but with a boundary as sharp and absolute as any recorded in the 4 billion-year history of life on this planet.